This is the kind of thing that people use in their professional life. This is actually... say something to me, don't worry about it. This is the kind of thing that you'll come across in employment. And it's a GPS system like the GPS systems that you have in your mobile phone or in your car, in the sense that we have antennas, that's what these domed boxes are, which are receiving signals from a group of satellites above our heads. And the way that it calculates position is by knowing where each satellite is, because it has inside it an almanac, a list of satellites' orbits and times. It knows where they should be, and it measures how long it takes for a signal to get from that satellite to the receiver. How does it do that? It does it because the signal itself has a time stamp on it. The signal is saying it's 4:27, and if it gets there at 4:28, it knows that it's taken 1 minute to get there. That's how it's doing the distance by time. Because it knows the distance to that satellite, and that satellite, and that satellite, and that satellite, at least 4 satellites, it's able to triangulate its position. And clearly, the further scattered those satellites are in the sky, the more separated they are, the better it's able to triangulate its position. Because if they're all just above us, the triangle that it's trying to create is very narrow, so its position isn't very accurate. So we're trying to get a place where we see lots of satellites to compare positions, scattered around us in the sky. Mamtor's a bit of a problem, because there are satellites over the horizon over there, beyond the mountain, but the signal isn't getting to us. So the distribution is going to be a little bit around this side of the sky. There'll be, I think we can say there are, of the American Navstar satellites, what we normally call the GPS system, there's something like 10 to 12 visible at the moment, all of which are going to be used for some part of the coordination. We're also seeing something like 5 or 6 of the Russian satellites, GLONASS. And we're picking up those signals too. In a couple of years' time we'll be able to pick up the European ones, Galileo too. By using all those together, we don't get very much more precise position, but we get coverage at times when, with one system alone, we wouldn't be able to get a position. It's not just measuring the time of flight of the signal from the satellites to here. It's doing something much more sophisticated. It knows the wavelength of the radio waves being sent from the satellites. And by comparing the 2 different wavelengths that each satellite sends, by interferometry, it's able to work out exactly which wave it lies within. That means that it can get sub-meter accuracy. And by doing that for all of the satellites around the sky, it gets down to the centimetre accuracy. Now it takes a while for the base station to average a position to that accuracy. But by comparing the errors measured here and using them to subtract from the errors measured here, it gets a very accurate relative fix on this rover. And so if this is precisely positioned and this is connecting a correct signal, we're able to get centimetre precision and accuracy in real time wandering around with that. And that makes that a very powerful tool. The biggest error in the signals that we get are due to the moisture in the atmosphere, which changes the velocity of the radio waves, and due to changes in the electromagnetic behaviour of the ionosphere. That changes the path length essentially. And towards the horizon in particular, the path length through the atmosphere of the signal is really very long. A satellite over there is grazing the Earth to get to the receiver here. And so satellites near the horizon we usually ignore because the path length is usually too inaccurate. But above about 15 degrees they're useful, all the way up to the zenith above us. So that's how it's working. It's recording the corrected signal between the two and storing it in the internal memory.